Okay, so today we want to talk about so today's lecture is more of a mixed topic. It's mostly going to be on thermodynamics, but along the way we'll be talking about some kinetic theory and diffusion. First law, hold on, so first off, let me talk about the dynamics, or some people would call the physical mechanics. So just bits and parts of it. We're not going to talk about the whole branch of like statistical mechanics. We're only going to be talking about a few things from here. So I think first off, one thing that you may have learned in SDPM or SPM is just the first law of thermodynamics. So this first law is just the conservation of energy. If you're in SPM, it's called the conservation of energy. If you're in SDPM, we'll like learn along more fancy names that. So it basically says that. So it basically has this equation. So that's basically it. You might see. So I'm pretty sure that you guys have learned this before. If you have seen this, can you put an emoji or something, just so I know everyone's on the same board? No one's okay. If you've never seen it, can you put an emoji? No one's reacting. Hey guys, do you guys want to complete OFM? Wait, I just want to see like how much detail I should give you guys. So if you have seen it before, can you react? So can you give me anything? Okay, one person has seen it. Okay, two people have seen it. Okay, so everyone else, if you've never seen it, can you give me a different emoji? But it's like totally fine to do this. If you have never seen it before, I will like explain it in more detail. Okay, so we will move on then. So, now, okay, so the long story short is that there are a few thermodynamic variables. So for a given system M, so for a given system, there are a few thermodynamic variables that are intrinsic to the system, which is like something that you can describe with a number. So this would be the internal energy, which is the total sum of energy. So over here, this U is the total energy. So it's more like the total average energy lah, because we have this idea of molecules bouncing around, having this energy, having like kinetic energy and potential energy. But it's the total average energy is the U. Right, the change in total energy. Whereas this dq with a weird line on it, it means it's the heat energy transfer. So this is something. So this is something you cannot control. This is something that's governed by the temperature differences. This is something you cannot control. Whereas here, it's something that the system can control. This is controlled energy. This is work done. So this is useless energy, and this is useful energy. Again, this classification is more of a free roll kind of thing. So like work done is more of a you have this drive. You have this like you want this energy to be done. For example, think of a battery. You want a battery to do energy. Think of a car. The work done is just the force times the velocity. I mean times the time rather. Like the power generated by the motor that pushes you forward. That's the work done. The DQ is something that you don't want. It's like the wasted energy. It's the useless temperature difference reservoir flow energy. So yeah, that's a fundamental philosophical classification of this equation. Total change can be decomposed into these two parts. There's one useful part and there's a useless part. So I think so. So for a system, again coming back here, we have these things called state variables. So what are state variables? state variables are variables which are intrinsic to the system. So, for example, internal energy is one, the volume of a system is one, how many particles in the system is also one, and so there are a lot more, but Q is not a state variable. The heat here is not a state variable. W is also not a state variable. So how do you know what's a state variable and what's not a state variable? So, what about the temperature? Temperature is also a state variable. This and then a lot more. So, like pressure. What else? I'll keep adding to the list if I keep remembering. Okay, so yeah, so for an ideal gas law, PV equals NKT. So K here is the Boltzmann constant. I don't know if everyone has seen this kind of version before because I know people have seen this version more often. So N is the number of moles, whereas this big N is the number of molecules. Same thing. But yeah, so this equation, I know you guys have seen this before. You can learn how to like derive the isothermal expansion or like stuff like that lah. So just to say, you guys have to know how to do this. We're gonna skip over it today. But yeah, like, the point here is to show you guys like what like the bigger picture here. The bigger picture here is that ideal gas are just a small model that you can test this equation. And so you can see here, everything here is a state variable. So P is a state variable, V and T are state variables. So okay, what are state variables? State variables are things that things that only depend on other variables in the system. It doesn't depend on the path taken to get there. So again, so if this is like space, right? If this is space, space. So if you draw it like this, you already assume that P and V are state variables because you use them as the axis. So that means that you can never use like heat as an axis because that's just not true because you cannot express states with heat. Heat is a path dependent thing. So the point is, if things are state variables, you can plot them. So if things are state variable, then one set of state variables correspond to one configuration of the system, and it's like a one-to-one mapping. Given the whole configuration, if you can fully describe a system, it gives you one state, and one state of the system can you can undo that to get. Actually, wait, no, it's not one-to-one. So it's like it's many to one because like there's some degeneracy there, but the point here is that one set of variables. So for example, P and V here, one set of variables. So normally what we do here is like when you have a PV, you can plot like these things, right, for the ideal gas law. So for example, there's 1 point, and this is like fixed temperature, right? Isothermal. For example, this is like one example that you see. Like what was called Boyle's law or something. So at fixed temperature, the set of these lines correspond to a set of different configurations of the system. So these are state variables. Whereas you can never see heat plotted on these graphs because it depends on what path you take to get there. And the path, so yeah, I'll just leave it at that. I think one more thing to say is that if you have so this is a state diagram, state like a PV. One more thing is that if you have a process that's cyclic, so for example, you start here, you go here, come up here, you come back up here. For example, Wait, let me just randomly draw it. So, so if you have a random cyclic process, so if you start here, you progress the system through a bunch of different states, and you come back to the same state. So this can be like a Carnot engine or like the type of engine that's cyclic process. The area enclosed over here is the total work done. The area enclosed is the work done for a PV system. For a PV gas system, the enclosed area in the state diagram is the work done. And why is that? So work done is W, right? W is so this is the net work done. The total, if you do useful work and then the system also does work against you, uh, this is the total work done. So why is this? So long story short, this total work done, I'll call it W net. So net work done. So you can think of it like this. Let me just go in the other direction so it's easier to draw. The direction also matters. The direction only tells you about the sign of the work done. But it's the sign of the work done. So how do I know this? So we know that work is negative P dV integrated. The work done by the system. So so when yeah, sorry. So then this will be negative work done. So okay, long story short, how do I know this? So if you start from here to here, this path, the area under the graph is just the whole thing, right? The whole thing over here, this whole area down here is positive or negative. Can someone tell me? If I define this as my work and I integrate from here to here, is the area under this graph positive or negative? So it's a question for you guys. If I define this to be my work and I integrate from here to here, positive or negative? Okay, I see one. I see one answer. Guys, I see someone says positive, and no one says negative. Oh, okay, unfortunately, because the answer is negative. So why is that? So this is so this is actually negative. Why? Because okay, over here we know that P is positive, right? P is positive, so this is positive. But dV, when they go from left to right, delta V increases. So delta V is also positive. So this is positive, positive. And if I integrate positive, positives, I should get positive. But then there's a negative sign here. There's a negative PdV, right? So over here, there's a negative sign. So therefore, the total area down here is negative. Right. So it's okay. But there's a chance to reclaim yourself. So when I go from here, I integrate from here to here instead. If I integrate from this end back to that end, what about this area under the graph? Is it positive or negative? This one should be positive, right? So why is it? Because now, even though P is positive, even though P here is positive, the dV, you're decreasing the volume. You're going to the left. So here, the work will be, so this would be, this is negative zero, sorry, this is less than zero, this is greater than zero. And if you multiply them together and integrate, you get something that's greater than zero. So, long story short, what I'm trying to say is that you reach one this. So the total area under this red line. So okay. Actually, wait. Do you guys know what I'm trying to do in the first place? Um, so work is the total integral of negative PdV, right? So imagine at every point along the trajectory, you bump delta V, you bump by the volume, you bump volume, you measure P, and you multiply the bump to the P. You add that to the total running start. So it's like over here, I measure P, multiply by dV, I add. Here I multiply by P, and then I add. So I multiply, add, multiply, add, multiply. So along every point on the boundary of this surface, I multiply by P dV, and then I add to the system. I add to this total work. And so I go along every point of the trajectory. Now I'm breaking out into two parts. Is that okay? So hopefully you guys see why I'm trying to do this in the first place. Okay, um, so that's why I can kind of break this out into two parts. One part, like when the system is still at on the top, and then another part where the system is at the bottom. And so when I integrate, I should get a top part which contributes a negative to the sum, and there's a bottom part which is a positive to the sum. And so therefore, you see that the difference when you actually add the total work together is negative because there's a negative area is bigger than the positive area. And so you add them together, the area inside is negative. So this is a negative area. So it's a negative total work done. So okay. Yeah, so yeah, that's the negative total work done on the gas, which is to say that the gas does work on the environment. Okay, so any questions on this? Okay, so one more thing, equipartition. So okay, let's move on to something else. Equipartition theorem. So the equipartition theorem states that if you have an energy that has a degree of freedom, so I'll explain later. So if you have a so okay, let me say this. So if you have a system for one given degree of freedom of the system, suppose it's I call this X. The energy, average energy of that degree of freedom, so there's a degree of freedom. It's gonna be, so for example, if this is like a power law, I'm just writing random coefficients. So this alpha is a random coefficient. If it's alpha times x to n, for example, if it's in this form, then the average energy is going to be kT over n. So that's the equipartition theorem. Okay, so let me describe what a degree of freedom is first. So a degree of freedom is how many independent things that you can change in the system. For example, if you have, if you have a gas molecule, so a gas molecule has velocity, right? Velocities have energy, so therefore, like velocities are a degree of freedom. But is it just total speed, the total magnitude of the velocity? No, it's not, because the degree of freedom here is what you can individually change. We live in a 3D world. We live in a world where we have three dimensions. So this velocity doesn't just have a magnitude, that would be speed, right? So there is a different distribution for that. But over here, the equipartition theorem says that for only one degree of freedom, that's like Vx, Vy, Vz. So these are individual degrees of freedom. The total speed is not a degree of freedom. So yeah, remember this. The individual Vx, Vy, Vz's are degrees of freedom. The total speed, the magnitude of this is not a degree of freedom. So okay, by the way, whenever I write this kind of brackets, whenever I write this kind of bracket, like dot dot dot, I say that I'm taking the average. I'm taking the average over what? I'm taking the average of over all possible degrees of freedom. So let's see how you do this. So let's see how we can show this. So the idea here is that so the idea here comes from a higher idea from thermodynamics. So, but from the Olympiad level, you don't have to know this. But from the higher thermodynamics, there's a few different philosophies in which people think about energy. Sorry, what not philosophy. Like there's a few different ways that people have models of thermodynamic systems. So there's if you want to learn more about this, there's a microcanonical ensemble. So which is to say that energy is fixed, and there's a canonical ensemble, which is when temperature is fixed. And then there's also a ground canonical, but if I remember correctly, this is just the chemical potential is fixed. So the long story short is that normally people work in the canonical ensemble because it's a closed system. So the grand canonical ensemble has things where like things have particle exchange. So imagine your gas is not like in the system. Your gas can leak outside, leak inside. So it's a little mafan lah. But over here, normally people you work in the canonical ensemble. You're a closed system, but the closed system can exchange energy with the environment. So that's the canonical example. Whenever we talk about ideal gas laws, we're working in the framework of a canonical example. So because you fix a temperature, but you can also vary the temperature lah. But like as in temperature is a thing. Temperature is something that you can control. So so over here in the canonical ensemble, the probability. So over here the energy is not fixed, right? Energy not fixed. But the temperature is something that's fixed, and you have a knob on this. You can fix this temperature from the outside. So in the canonical ensemble, the probability of a system having an energy E is proportional to exponential negative E over kT. So this is called the Boltzmannian probability. Boltzmannian probability. There's a whole proof behind it. Just don't worry about it. You will not be tested on this on OFM. What you will be testing on and like related things. I mean, not just in OFM, but like I4 and if you do astronomy, there's also IOA. Just at high school Olympiads, you should be expected to like know that this kind of thing exists. It's like there's a distribution depending on how much energy you have. So it's not that when the system only has energy E, it can only have energy E. This energy E is the average energy E. Remember when we said internal energy is a total average energy. Internal energy is a total average energy. It's not to say that a system cannot have 10 U. It's not to say, so if I say a system has U, it doesn't mean that individual particles cannot have 10 U. An individual particle can have 10 times the average energy. It just has a really, 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 really small probability. And what is that probability? You can actually calculate with this, P of E, the Boltzmannian probability. So let's see. If you want to prove this, you can do it like this. Alpha x to the n times the probability x. Then you normalize by the integral of the probability. Does that make sense? How I wrote this equation down. If it doesn't make sense, can you please raise your hand? Or just send me a private message. Because I'm low on time and I'm not sure if I should give this more detail. Okay, so it looks like everyone's okay with this. So this equation is trying to take the average of the energy. This is the energy, and this is the probability times the energy. So it's like the expected value of alpha x to n, and then normalized by this is not normalized. There's no normalization constant here yet. So I normalize by this integral. And so this is why we call this a degree of freedom. If it's not a degree of freedom, we can't do this. A degree of freedom only works as a degree of freedom if we can integrate it as an independent variable. So that's why we have this like mental distinction of what's a degree of freedom and what's not. So, anyways, once you do all the math, this should turn out to be kt over n. It does not depend on alpha. It only depends on n, the scaling exponent of the degree of freedom. So over here, for example, if you have an example of like half kx squared. So where have you seen this before? Oh wow, it's a spring energy, a spring constant times the. So for example, this is the elastic potential energy. This will give you kt over 2. So if you have half mv squared, this will also give you half kt over 2. And the 2 comes up here. The 2 comes from the exponent. The 2 here comes from the exponent. So that's therefore there's 2 here. And so, for example, if you have a spring system, where the total energy is like half mv squared plus half kx squared, that means that the total average energy is just kt. So you just add these two things together. Okay, what about, so this is like a one-dimensional. If you have a three-dimensional free particle, if you have just so this can be written as vx squared plus vy squared plus vc squared. So over here you have 3 degrees of freedom. There's a vx, vy, vz if you're in 3 dimensions. So therefore there's going to be 3 times kt over 2, which recovers the normal 3 half kt lah, which is what you should see from your high school or STPM textbook. So until this point, is everyone okay? I must say, in the past few years, OFM has been less inactive. OFM was more active. I'm not sure what's happening today. Maybe it's just that everyone has had lunch. So, maybe from coma. Sorry. So, what else? We have? Okay. So if no one has questions, we'll move on. One more thing I want to talk about is diffusion. And kinetic, let's talk about kinetic theory in general first. Kinetic theory. And then we'll talk about diffusion. So kinetic theory is basically using this idea of a Boltzmannian probability. So previously, we know that if you have 1 degree of freedom, for a given degree of freedom that constitutes an energy E, the probability of the system being at that energy, given that you fix the temperature. So over here, the reason why we talk about this like canonical, microcanonical bullshit is because over here, because the temperature is fixed, we can say that there's this temperature. So this is fixed in the canonical. So this T is fixed in the canonical ensemble. So in the kinetic theory, essentially, there's this distribution called the Maxwell-Boltzmann distribution. Any chemists in the crowd? So if you're taking chemistry, you will definitely you will definitely have seen this before. Chemistry in A levels or STPM, you will definitely have seen Maxwell-Boltzmann. And what this equation says is that so it's a distribution of particles with a speed. So before that, we were talking about velocity, right? So over here, whenever we said, so because in a 3D system, there's Vx, Vy, Vz. This is not a degree of freedom. These 3 are. But the Maxwell-Boltzmann distribution gives the distribution for this. How do you do this? Something about like energy is half Vx squared, Vy squared, Vz squared. And this is the only energy that's relevant. Whenever you talk about Maxwell Boltzmann distribution, you don't talk about potential energy, you don't talk about so it's like ignoring all potential energy. That's the assumptions of ideal gas. The ideal gas assumption, one of the ideal gas assumptions is that there is no interactions between the molecules, right? If there's no interaction, that means there's no potential energy. So and like ignore gravity and whatever, but that's it. So over here, how can you think of it? Like so you know that we want a distribution in terms of V, which is the magnitude of all that. We want a distribution in terms of V. So for a fixed V, how does that look like on a three-dimensional plot? So Vx, Vy, Vz, right? If I say that, okay, I only want to look at some configuration of Vx, Vy, Vz, some combination, such that the V squared is a constant. So what kind of surface would that be? Think about it. So let me reframe the question. The problem here is that this one, this two, this three, so Vx, Vy, Vz are degrees of freedom, but this is not. So my question to you is that if I fix this number, how would that look like in the space of Vx, Vy, Vz? So think about it for a second. And once you have an answer, you can send me a private message. Okay, so I did see a few responses, and yes, it does look like a sphere. So if you wanted a sphere, you got it right. So why is it a sphere? Because it will be a sphere in this Vx, Vy, Vz space. Exactly. So yeah, you don't have the back if it does say a sphere. So why is it a sphere? Because here, this is the definition of the magnitude of the velocity, right? The magnitude of the velocity is defined to be the normalization, the norm of the velocity vector. It's Vx squared plus Vy squared plus Vz squared. And so if I just kind of like change variables now, if this looks very, very foreign, let me just change variables here. So let me change variables. So this is not really true. I mean, like, I'm not trying to say this. I'm putting quotes here just so you like make analogies, but hopefully you guys have seen this. R squared equals x squared plus y squared plus z squared, and know that, oh, that corresponds to a sphere. That means that a sphere in the velocity space with a fixed radius gives you a fixed velocity. And so the probability is not just one dimensional now. The probability is not just in one dimension. The probability is in three-dimensional space. And so you have to multiply by how many degeneracies there is. So when I say degeneracy, it means that like uh, how many how many how many states give the same energy. So um, if every point on this sphere, if every point on this sphere also gives the same energy, That means that there's a total of 4 pi v squared that gives the same energy. And why is it 4 pi v squared? 4 pi v squared is the surface area of the sphere. And the surface area counts how many points on this sphere you have to make up the total area. So it's a measure of how big this area is, if you may. And so therefore, the probability of just one velocity is going to be 4. So it's not going to be equal because there's still some normalization constant. Oh shit! So this would be the Maxwell-Boltzmann distribution. Again, this is not a full distribution because this is not an equal sign. This is a proportional to sign. It's a proportional relation because there's some normalization constant here that we haven't talked about yet. But if in math, you learn how to normalize distributions, right? So I'm not going to talk about how to normalize the distribution here. But yeah, the point is that this is the Maxwell-Boltzmann. And so with this, you can talk about how particles bounce around, statistics in general, stuff like that. Yeah. So, any questions? Okay. Diffusion. So. So, diffusion is something that's probabilistic. Diffusion is something that comes from statistical dynamics, and it's one of my favorite topics. So, why is it? Diffusion is a way of letting things move without actually making them move. So, it's like a, so it makes so even though all the equations here are reversible, right? All the equations here are reversible. For example, when you look at circuits, so this is from one of the past lectures. If you look at circuits, if you give a capacitor a voltage, the capacitor can undo that voltage because if you charge a capacitor, it uncharges a capacitor. But for a diffusion system, so the capacitor example is to say that the laws of physics are reversible. If you charge a capacitor, it can discharge. If you charge an inductor, it can discharge. If you push a spring, the spring can the spring can retract. So the laws of physics are reversible. If you spend energy to push a box, you can also reverse. You can also reverse time to say that if the box pushes me, I get energy. So imagine a car, imagine a really fast moving box, collides with you, you collide with a box that's moving really quick, collides with you, you gain energy. But you can also reverse that and say that you push the box with a lot of energy. So lots of this are reversible. So diffusion is a way of using these reversible laws to create irreversible conditions. So let's look at a model of diffusion. So suppose you have one particle, and this particle. Let me put my notes. This particle has velocity at time t. Suppose this particle has a velocity at time t. And at every random time t, so I discretize time. I make time discrete. So instead of time being on an axis, of a continuous axis, I break it up into small chunks. 0, delta, 2 delta, 3 delta. I break time up into different pieces. Let's say that this is V1, V2, V3. So these are all random variables. I'm trying to say that diffusion, at the end of the day, comes from a probabilistic nature. you can um, so um, so these this VNs, so these VNs are random variables. So think of it like this: you toss a coin. The first time you toss it, I call it V1. The second time I toss it, I call it V2. The third time I toss it, I call it V3. So the coin tosses are random variables, but they all come from the same underlying source. So like V1 will be like the first coin toss, V2 will be the second coin toss. Sorry, fella. I'm also kind of sick on this trip. Uh, okay, so random variables. So like yeah, if you toss a coin, if you toss a coin n times, then the first time you throw it, I call the result like V1. The second time I throw it, I call it V2. So these are like random, like they're not correlated. So if they're not correlated, Vn is zero, right? The average velocity, because everything is like probabilistic in the positive and negative direction, right? If I randomly throw a coin, if I randomly throw a +1, -1, if I randomly throw a fair coin, it can be +1, -1 with equal probability. So the average is a zero. What I also assume is that the correlations between different velocities is also zero. The average of the correlations is also zero, but except for the fact, except for when they're the same. So if they're the same, I call it some. So normally, and when n is equal to, so for two random coin tosses, n and m, when they are, I'll assume that they're normally zero, and n are different. But if they are the same, if n is equal to m, then like for example, think of a coin toss, right? If I take this like +1 -1, I square it, I get 1 and 1. So the average is not zero anymore. The average is something positive. So therefore, I call this a number C. I don't know what C is. I'm just calling it C. So this is our framework lab. Suppose so right now I'm trying to show you how diffusion comes out. Diffusion comes out if you think of like velocities being randomized. Diffusion comes about when you think of velocities being randomized, because right, like when you think about the Brownian experiment is to say that the pollen grain like moves randomly, like it's like zigzag motion, right? So the velocity is like randomized over time. So with this framework, so what's the distance? So the average displacement. So displacement, displacement. So the displacement is going to be the total sum. It's going to be like v1 times delta plus v2 times delta plus dot plus vn times delta, right? Does this make sense to everyone? I'm just taking velocity times time, velocity times time, velocity times time, all the way until like my time of interest. So suppose my time of interest is, let me see. Suppose I say I want to look at t equals big N delta. Then delta t of delta x of t is just going to be v1 times delta plus delta plus v big N. So that's going to be delta times the sum of v small n. If I take the average, if I take the average of the displacement, I get delta times average of n. And since this is zero by assumption, remember here, this is 0 by assumption. Average displacement is also 0. Which is kind of weird. The average displacement is 0? How's that mean? Okay. What's that mean though? Let's look at something else. Let's look at the average displacement squared. The mean displacement squared. So the mean displacement squared. So how do I square this? Sorry, actually before that, like, why do we even want to look at a square mean square? Why do you want to look at the? Why do we even want to look at displacement squared? The reason why is because when you learn probability, there's two numbers that's related, right? There's a mean and there's a variance. So motivated by the fact that even though some probability distributions have 0 mean, the variance doesn't have to be 0. The variance can be positive. And so, for example, if you think of a Gaussian distribution, this is P of X, Gaussian. So this X has a 0 mean, but it has some width to it. So here the width is the variance. So over here, therefore, it suffices for us to be motivated to look at delta X squared. So over here, I can say that this is delta sum over n multiplied by sum over m. So remember here, when you multiply to sum, you have to multiply them. You have to use different indices because these are not the same index. Here, I will get a delta squared up front. And this is how I just pulled out the delta squared. I rearrange the sum. I get this. And so over here, this average. What is this average? This average says that so this sum, the mean squared displacement, is going to be related to this thing called the correlation. The correlation between velocity. The velocities are mostly uncorrelated. They're uncorrelated except for itself. So it's only correlated to itself. So this is only equal to. So suppose I fix an n, right? So for a given n, for one given n, there are many m's that I sum over. So what's the only m that gives a non-zero contribution? The only n that gives a non-zero contribution. So the only m that gives a non-zero contribution at a fixed n is when they're equal. And so when they're equal, it's just it's just C. The correlation is just C. So therefore, this is going to be delta squared C times n. And so what's n delta? N delta. N delta is what we call the time because we discretize the time. So n delta, since we discretize the time, this is T. We see, so it's C delta T. So that's what we call the actually. Okay, sorry. Oh my god, there's a huge spider. Nice. Good morning. That's something like that. This is what happens when you get to Africa. So many really critters. Okay, anyways, yeah, what I'm trying to say, what I'm trying to show you guys here is that for I'm trying to show you guys here that the mean square displacement. So normally when you have a normal velocity, like when you're moving, you say v, your displacement is just vt, right? If you're just normally moving, the displacement is just vt. But when things diffuse, this is 0. The displacement is 0. What is non-zero instead is the delta x squared. this delta x squared is going to be something times t. And specifically, this is 2dt. I'm going to spoil it for you. This thing is actually 2d. I'm just going to spoil it. Like, just like, I'm not going to show you guys where this comes from. I'm just going to say that. I'm just going to say that, like, this is defined to be 2d. So the d here is called the diffusion constant. So diffusion coefficient. It's normally like 10 to the -7 or something like that, if I remember, for like random molecule. But yeah, that's how diffusion works. Diffusion works very differently from how normal directed motion works. Directed motions depend on this, like just v times t. Because if you have a fixed velocity, you're moving in one direction, so dt. But because diffusion depends on like random, like different directions and stuff, it's gonna have this. It's gonna be a little different. It's the square. It's the mean squared displacement that is proportional to time. So remember this. Yeah, I think I'll stop it here. If you have any questions, I will be in the Zoom to answer them. But yeah, thank you for watching. For people watching on YouTube.